In the first part of the lecture, we looked at an example of a greedy heuristic that gave us a rather poor solution in comparison to the optimal solution. In this part of the lecture, we're going to look at an example of a greedy heuristic that gives us the optimal solution. We're going to consider what's called the activity selection problem. In this particular problem, we are given a set of activities. A, here A1 to AN, just indicate the individual activities. Each of these activities has a known start time and a known finish time. And these times satisfy the rather obvious requirements that the start time must be at least 0, the start time must be less than the finish time, and the finish time must be less than infinity. We say that two activities are compatible if they do not overlap in time. So for any two activities I and j that are compatible, then either the finish time of activity j is at latest the start time of activity I, or the finish time of activity I is at latest the start time of activity j. So the problem is to determine the maximal number of compatible activities that can be selected. So you have to determine the largest subset of A that contains only compatible activities. In this approach, greedily selecting compatible activities in order of increasing completion time will give you the optimal solution. And we will see why this is the case in the coming slides. The activity selection problem has a number of practical applications. So one example is machine scheduling, where you might wish to perform the greatest number of tasks on a machine. Another example is timetabling, where you would like to determine the largest number of lectures you can hold in an auditorium. To help illustrate the greedy heuristic that we're going to look at, we're going to consider a small activity selection problem. In this particular example, we have 11 activities. What you see at the top here is a list of these activities together with their start and end times. So activity 1 starts at time 8 and ends at time 12. What you see down here is the same set of activities, just ordered by increasing finish time. So activity 7 is the earliest one to finish at time 4, and activity 10 is the latest one to finish at time 14. The activity selection problem asks us to determine the largest set of compatible activities out of these 11 activities. Obviously, we can't select activities 7 and 4 because they overlap in time, but activities 7 and 10 can be selected together because they do not overlap in time. To help illustrate the greedy heuristic, I've put together a Gantt chart to sort of define this activity selection problem. Here we see the 11 activities as bars on this Gantt chart. The length of a bar is just the duration of the activity, and each activity obviously, or the bar for each activity, starts at the activity's start time and runs until the end time. So activity 7 started at time 1 and runs until time 4. The greedy heuristic says that we should select activities in order of increasing completion time. So we start by selecting activity 7. If we select activity 7, then we cannot select any of the red activities since they conflict with activity 7. We then look for the next compatible activity that is closest to the end time of activity 7, and this happens to be activity 11, so we select that. And this results in 2 more activities being unavailable since they conflict with activity 11. Okay. The next activity we can add is activity 6. This removes activity 1 from consideration because that conflicts with activity 6, and we can finally select activity 10. So the blue activities here are the ones that define the largest subset of compatible activities. Note there is also an alternative solution in this case where we can exchange activity 7 with activity 4. So there are, let's say, 2 solutions in this case. So what can we see so far? Well, I've shown you that the greedy approach returns a solution with 4 activities. I've shown you that there's another solution that is not returned by the algorithm having 4 activities, but our claim is that 4 activities is the largest number of compatible activities that we can find in this case. But how do we know that 4 is the optimal number in this case? Well, intuitively, it seems like kind of a smart thing to do, right? If I consider them in order of increasing finish time, then I'm leaving the most time for the remaining activities. So the greedy choice will sort of maximize the amount of unscheduled time remaining, but we still have to prove that it is optimal. You might remember at the start of the lecture, I said that a heuristic does not provide you a certificate of optimality, nor does it provide you a certificate of quality. So without a proof in this case, we have no guarantees as to the quality of this solution. So let's try and prove that this is in fact the optimal solution to this problem. The proof comes in two parts. In the first part of the proof, we're going to show that there always exists an optimal solution that begins with a greedy choice. So there will always exist an optimal solution that contains the activity with the earliest finish time. In the second part of the proof, we're going to show that if we remove the activity with the earliest finish time from the solution, then what remains is the largest set of compatible activities that is also compatible with the activity that has the earliest finish time. So let's look at part one first. We're given a set of activities here. The activities are already ordered by finish time. So activity one has the earliest finish time. We suppose we have an optimal solution S to that problem, where S is a subset of A. If the first activity is part of that set, then we're done. So the optimal solution contains the activity with the earliest finish time. If it's not, then what we're going to do is construct an alternative solution that uses activity one that has the same cardinality as S. So if the first activity is not part of S, we then sort of denote the first activity in S as activity K. Okay, so the first activity in S is going to be called activity K. We're going to make a new solution by removing activity K from S and putting in activity 1 instead. This must be possible since A1, activity 1, is the activity with the earliest finish time. It can finish no later than activity K. So whatever activities activity K is compatible with, so is activity 1. Okay, so by doing this, we obtain a solution that has the same cardinality as S. And this sort of completes the proof. This shows that we can always find an optimal solution that begins with a greedy choice. If it doesn't, we can always swap it in and obtain something with the same objective value. The second part of the proof is maybe a little bit trickier, but it's in a similar style. We still have S, which is our optimal solution to the activity selection problem. So it's a subset of the activities in A, and it contains the first activity. We're now going to construct S prime, which is the solution minus the first activity. Okay, so we remove the activity with the earliest finish time. Then our claim is that this set is the optimal solution to this activity selection problem, which is the problem of determining the maximum number of activities, maximum number of compatible activities that is also compatible with activity 1. Okay. So if I remove A1 from the problem reduces to finding an optimal solution for the activities that are also compatible with the first activity. So let's suppose that we now solve this problem and we come up with a solution S prime prime. So it's a set of activities that are all compatible with the first activity, and that the cardinality of this set exceeds this set. Okay, and we know the cardinality of this set is just the cardinality of S minus 1 because I'm removing one activity. I'm going to show you that this must be impossible, because if that were true, I could always add activity 1 to that set to give me a solution to the original problem. Okay, if all of the activities in S prime prime are compatible with activity 1, and this set has a cardinality larger than this set, then I can always add the first activity to that set and get a larger set of activities than what is contained in S. Okay, and that can't be true because our assumption was that this is the optimal solution. So we get a contradiction, and this shows that the optimal solution to the problem of determining the number of activities that are compatible with the first activity can be obtained by just removing the first activity from the solution. Okay, so the correctness of this proof follows by induction on the size of S. What we've considered here is just the first activity, but the exact same reasoning could be applied to the case where I remove the first two activities in S. What remains then must be the optimal solution to the maximum number of compatible activities that are also compatible with the first two activities in S. Okay. So some comments on the activity selection problem. At every iteration of this greedy heuristic, we are solving a problem of the same format as the original problem, having one fewer dimensions, right? We are adding an activity to our solution, and then the next sort of step or subproblem in the heuristic is considering a smaller version of the same problem. The problem itself has what's called the optimal substructure property. What is that? Well, this says that I can obtain the optimal solution by just sort of collecting the optimal solutions to the individual subproblems that I consider. And in this case, our subproblems are which activity to next put in the solution set, right? So the next compatible activity with the last added activity. So the optimal solution can therefore be obtained by making a sequence of locally optimal solutions, making a sequence of locally optimal decisions to ultimately obtain a globally optimal solution. And if you compare this to the NASA example that we had in the first part of the lecture, we were also making locally optimal decisions. We were picking the mission with the largest ratio, but this did not ultimately lead to a globally optimal solution. Okay, so these are two important properties central to the success of greedy algorithms. We need the optimal substructure property, and that we can make a sequence of locally optimal decisions to ultimately obtain this globally optimal solution. Okay, but now let's look at another way. Suppose we wanted to apply mathematical modeling to this particular problem. Is there a way we could formulate the activity selection problem? So let's look at a graphical representation of the problem. Here you see what's called a conflict graph. There are 11 nodes in this graph, one for each activity. They're numbered 1 through 11. And you will see an edge between two activities if they are in conflict. So if the activity times overlap with each other. So the problem here is to determine the largest number of activities that are not incident on the same edge. Okay. So let's have a look at how we might go about defining a mathematical model for that. Well, we're going to define some binary decision variables, xj in this case. Xj is going to equal 1 if activity j is selected, where j is running from 1 to 11. We have 11 of them. It's going to be 0 otherwise. And we're just looking for the largest number of activities, so we're going to maximize their sum, 1 through 11 of xj. And we know the following constraints must be satisfied. xi plus xj must be less than or equal to 1 for all incompatible activities I and j, and all in any pair of incompatible activities is indicated here by an edge. So we will have one constraint for every edge in this graph. Our decision variables are also binary. So we are looking for the largest set of nodes in the graph such that any pair of nodes in the solution is not incident on the same edge. Okay. This is the solution to that problem, and you will see we pick activities 6, 7, 10, and 11. The color is not so great, it seems, but you can see that no two nodes in the solution are incident on the same edge. And here we have the Julia implementation of this. It's a little bit different to maybe what you've seen earlier, but we sort of work with maybe more object-like structures here. We have activities, And within an activity, we have a start and finish time. I have an array of these, and you can see the start and end times of the activities match the example that I gave you. We set some parameters. We set a parameter n, which is just the length of this activity array. We define a model. We have a binary variable now associated with each of the activities here. So that's what sort of this construction says here. Our objective is now to maximize the sum of the binary variables for all of the activities we have. Down here, I am building the constraints for my model. It might be a little bit different to what you've seen previously as well, but here I'm constructing my constraints in a loop. I'm looping over all pairs of activities. Okay. I'm looping on the outer loop here from I equals 1 to n minus 1, and on the inner loop, I'm looping over j equal to I plus 1 to n. This is just to ensure that I only consider I and j and not also j and I. Down here, I have a check to see if the two activities that I'm considering are in conflict. So I look to see whether or not the finish time of activity I is at latest the start time of j, or if the finish time of activity j is at latest the start time of activity is at latest the start time of activity I. Okay, and if it's not either of these cases, then they must be in conflict. Okay, I optimize the model and I can print this solution. So if you were to run this, you would get the optimal solution that we just looked at. Okay, that ends part 2 of the lecture, and in part 3 we're going to consider another example.